Go. And so I'm going to be going back and forth between this and the paper I'm writing on. And we'll go ahead and get started here. Okay, so often the boron in compounds does not have an octet. Show this by drawing the Lewis structure of BH3. This is unlike nitrogen in NH3, which does have an octet. Show this by drawing the Lewis structure of NH3. So I'm going to switch screens and we'll do the first two parts, which is basically to draw the Lewis structure of BH3 and of NH3. So for BH3, we've got 3 plus 3 electrons for 6 total. And we're going to put boron in the middle because it likes to make 3 bonds. And we're going to put the hydrogens on the outside. So you can see here, we've used all 6 electrons. So it's going to be impossible for boron to have an octet. For NH3, however, we've got 5 electrons for nitrogen and 3 for the hydrogens for 8 total. We'll put nitrogen in the middle. And this is how we start NH3. And we've only used 6 electrons, but we need to use 8. We don't put octets on hydrogen. They only get the single bond. So what do we do with the extra 2 electrons? You put them on the nitrogen. And there's your 2 Lewis structures of BH3 and NH3. Okay, so I'm going to go back to the homework so we can look at the rest of the problem. The boron in BH3 can achieve an octet by making a coordinate covalent bond to the lone pair of nitrogen in NH3. A coordinate covalent bond is formed when both bonding electrons are supplied by one atom and no electrons are supplied by the other atom. This is the most common type of bond formation in organisms. Draw the compound formed when BH3 forms a coordinate covalent bond with NH3. There's a little extra thing at the end there. I'm not sure where that's from, but regardless, let me show you what I'm asking for. So I'm going to draw these again, but I'm going to draw them a little bit differently. I'm going to draw them like this. Now, a very common thing in chemistry is to show how electrons are moving around in chemical reactions. And to show how they're moving, you use an arrow. So you also make it a curved arrow. So whenever you see something like this, it means those electrons are staying on that atom, but they're connecting to that one. And by connecting, I mean bonding. So here are those electrons that used to be a lone pair, but now they're a bonding pair. And this is called a coordinate covalent bond. And that's all I'm asking you to do. And number 1 is to show me that. And why does this molecule work? And the answer is because the boron has an octet, the nitrogen has an octet, and the hydrogens have their duets. And so it's a fairly stable compound. Any questions about number 1?
No, I think I'm good.
Okay. So you may remember the chart I gave for how many bonds these atoms like to make. The number of bonds of lithium would be 1, beryllium would be 2, boron 3 or 4, carbon 4, nitrogen 3, 2 or 4, oxygen is 2 or 1 or 3, and fluorine is 1. try and center those a little bit better. But so here's an example with boron making 3 bonds. And here's an example with boron making 4 bonds. And here's an example with nitrogen making 3 bonds. And here's an example with nitrogen making 4 bonds. Okay? All
Yep.
right. We're going to do a new share and look at the next problem. Okay, so I'm going to raise that to the top of the screen there. In which of the following compounds or ions does the central atom obey the octet rule? You can see for the first one, there is no real central atom. So the question is, do both of these obey the octet rule? And then the second question is, are any of these species, and that means these particular formulas, odd electron molecules or ions? Now, the reason they're called species is because we can't say molecules because they're not all molecules, and we can't say ions because they're not all ions, so you say species. So for number 2, let's look at these one at a time. I'm going to write the formulas down before I switch screen. It looks like ClO2 is written down twice, but in the second one, it's got a charge. Okay, so I'm going to do a new share here. And you can see that I have written all of the formulas down. So with NO, we've got 5 plus 6 electrons for 11. So this is the way it starts. Of course, they're bonded together with a single bond to start with. We put electrons around the oxygen first because it's more electronegative. And here we've used 8 electrons. So now we're going to put the other 3 on nitrogen. So 1, 2, 3. Now we want to get an octet on nitrogen if we can, but we really cannot. The best we can do is this. So we have 2, 4, 6, 7 on nitrogen. I want you to recall that in period 2, you cannot have more than an octet. And sometimes you have less. So here's nitrogen with less than an octet. So this is an odd electron species where nitrogen does not have an octet. Okay, now for SF4, we've got 6 plus 4 times 7. 4 times 7 is 28, if I remember right. Plus 6 is 34. I was thinking there were 5 fluorines, but there's only 4, so oh well. So here I'm putting lone pairs on the fluorines because they're the terminal atoms. And with 4 of these and 8 per, I've got 32 electrons, so there's 2 more on the sulfur. Okay, so if we analyze this with formal charges, we're going to find out it works out pretty good. In fact, if we analyze this with formal charges, you get a 0 here and a 0 here. If you analyze this with formal charges, you get a 0 here, a 0 here, a 0 here, a 0 here, and a 0 here. So, you know, we like this structure based on formal charges. So this one, the sulfur is hypervalent. We could actually call nitrogen hypovalent, but I don't think anyone ever uses that. Hypervalent means more than 8. But we don't have any odd electron atoms in here. Ammonia, we've already seen already, so I'm just going to straight out draw it. And we have octets where we need them in and duets where we need them. So there's not much to say about this one. SO3 is going to have 6 plus 3 times 6 for 24 electrons. And you're going to put sulfur in the middle and the oxygen on the outside, because sulfur can make more bonds than oxygen. So when I do this, we have 24 electrons. And we want to do a little better, so we're going to do this. And this is better than what we have above. But when we look at formal charges, this would be a 0. This would be a minus or plus 2. This would be a -1, and this would be a -1. So when we look at formal charges, we really don't like this structure. But it's better than this one, where this would be a -1, a -1, a -1, and a +3. So you can see by creating a double bond to this oxygen, we made the formal charge on sulfur better. Well, guess what happens if we do it twice, or 2 more times, I'm sorry. We still have 24 electrons, but the formal charges are all 0. So this is the structure we're going to draw. And again, sulfur is hypervalent. Now, if we look at the number of bonds each atom likes to make, if we look in the third period and we concentrate just on the metalloids and nonmetals, so we look at silicon, and that's beneath carbon, then you look at phosphorus, and then you look at sulfur, and then you look at chlorine. Silicon can make 4 bonds normally. Phosphorus can make 3 like nitrogen, but can also do 5. Sulfur can do 2 like oxygen, but also 4 or 6. And chlorine can make 1 like fluorine, but also 3 or 5. So in the third period, you'll notice the exceptions always go up by 2, 3, 5, 2, 4, 6, 1, 3, 5. So here we have a sulfur with 6 bonds, and it's hypervalent. Okay, so now I'm going to cross the ClO2 off and cross this one off, and I'm going to kind of shove these over and write this ClO2 here. So here we've got 7 plus 2 times 6, which is 19 electrons. So we know that oxygen likes to make 2 bonds and chlorine likes to make 1 bond, but in this case, oddly enough, the chlorine is going to go in the center. So this is one of those ones where you choose the less electronegative one to be the central atom. So we're going to draw this like that. We'll put electrons around the oxygens. And so here you have a total of 16 electrons, 17, 18, 19. And chlorine can be hypervalent. It can have more than 8 electrons. Here it has 2, 4, 6, 7. So this would be better. Formal charges here would be 0, 1, 2, 3, 4, 5, 6. So here you have an extra electron to be, or less than an extra electron. So you would have this. And you can see that if you look at the formal charge on this one right here, this is actually +2. By making a double bond to this, you do a little better. So this would even be better. And this is what I would say is the Lewis structure for this one. The formal charges on each of them is 0. And this is one where you're going to have odd electrons, and chlorine is hypervalent. Are we good so far?
Yeah, for the chlorine atom, so it has 4 bonds plus the lone pair on top, and then the
Yeah.
the single pair. Like, what is that considered having? Because it doesn't. That means that it's not really, but it's typical, right? You said it's
It's not
typically like
typical.
1 bond, 3 or 5, so it's
So
not either of those.
why do I choose this though over the say this?
Um, let's see. What are the max amount of electrons that chlorine can have around it?
14.
14, right? Okay. Yeah, that's what I thought. It's the same as sulfur, right? 14.
Yeah, anything in period 3 can have 14 electrons. Normally they don't. They might have 12. But
Okay,
why is
so
this one?
because
Why
it
do I
has
say this one
11.
is? Why do I say this one is better? Even
Yeah,
though this
because of
one,
the formal charge.
right? You're going to use the electroneutrality principle, which basically says you want the electrons spread out as much as possible. And the way formal charges help you to see that is if all the atoms have a formal charge of 0, it means that the electrons are shared pretty evenly.
So that supersedes any like status quo amount of bonds. And I
Right,
think it's more important to just know the amount of electrons that a atom can hold then.
right, right.
Okay.
So here you can see when I get to these, I say, oh, look, the formal charges are all 0. And then I say, oh, and look, it's got 6 bonds. But my
Okay.
focus is on, hey, the formal charges are great.
Okay.
Okay. And ClO2 minus, we're going to have 20 electrons, I believe, because if this has 19 with a negative charge, it should have 20, right? Starts the same way. There's 16, 17, 18, 19, 20. And here you'll see that the formal charges are -1, -1, and +2. So this is another one where this is going to be better. Because all the formal charges are 0, and this one's a -1. Actually, I take that back. This is not a +2, it's a +1. So this one looks pretty good, but this one is better. So in this one, the formal charges are 0, 0, and -1. And this one is better. So why is this one better?
Because the negative is on the most electronegative
Correct.
atom.
And it turns out there's another one of these. What's the other one look like?
It's the opposite. It's the same, but the
Okay, and
opposite.
I understand exactly what you mean. So the chlorine looks exactly the same, except for the double bond is on the other side, right?
Mm-hmm.
And of course, with these bad boys, we're always supposed to put brackets in the negative charge, just like we should do. Well, this is the only ion one. Okay, so
Okay.
this one, where we have 2 double bonds to the oxygens, is not as good because the formal charges rule. And this is one of the ones where actually the formal charges work with the number of bonds that they normally make or could make, right?
Okay.
So here we have the 3 for chlorine. Oxygen normally makes 2, but it can do 1, 2, 1, or 3. So this works out pretty well. So -1, 0, 0. So that's number 2.
Okay.
So you can see these questions are designed to make you think deeper than just what the book says with their examples, as it were. Okay, number 3, consider a series of molecules in which carbon is attached by a single covalent bond to atoms of second period elements. So we're talking about a carbon-oxygen bond, a carbon-nitrogen bond, a carbon-fluorine bond, a carbon-boron, and a carbon-carbon. We didn't do any of the elements that were further to the left, like beryllium or lithium. Place these bonds in order of increasing bond length without looking up the values. Okay, so here we have carbon-oxygen, carbon-boron, carbon-carbon, carbon nitrogen, and carbon fluorine. So how are we going to decide these bond lengths? And the answer is you're going to decide based on the size of the atom. So I'm going to put these in order in which they appear on the periodic table. Here's boron. Here's
Can
carbon.
you switch your screen?
Oh, thank you. I'm sorry. Okay, so we're looking at these 5 bonds, and we want to put them in order of increasing bond length. So I'm going to take each of these atoms and put them down in the order in which they show on the periodic table. Now, what do we know about atom radius when we go from left to right? Well, this is what they do.
It's smaller.
Right. And so here, my smaller is exaggerated. They don't get smaller like this fast. But it is obvious from my drawings that fluorine is smaller than boron, right?
Right.
So let's draw carbon down 1, 2, 3, 4, 5 times. So these are all supposed to be the same size. And I think I did a pretty good job of making them all look the same size. And these are all carbons, right? So let's draw boron next to the carbon. And I'm going to draw the boron as being larger. So the bond length goes from center to center. All right, now let me draw another carbon here. So here, these are supposed to be the same size. And here is the bond length from here to here. For a nitrogen, I'm going to draw an atom that's a little bit smaller. And here's the bond length. And then for oxygen, something that's even smaller yet. So here's the bond length for my oxygen. And for my fluorine, which is really tiny, there's my bond length. So the deal here is that you should see that that's a BC bond length. This is a CC bond length. This is an NC. This is an OC. And this is an FC. Are these lengths getting smaller? What do you think? Okay, so we're supposed to put them in order from short to long, right? So we're going to say CF is shorter than CO is shorter than CN is shorter than CC is shorter than CB. And that's how you would come to that conclusion. Any questions about that?
No, that was pretty straightforward.
Yeah, I think so. And especially when you draw the little figures. And when I
So
put
we
all my
should be
carbons,
thinking about radii when we're working on a problem like number 3.
yeah. And you know, when I draw it this way, where the carbons are all lined up the same, you can definitely see that the length gets smaller and smaller. And the point is not to make the atoms the correct size, but to make them relatively the correct size, whether one's bigger or smaller.
Right. And here they're all in the same period.
Yeah.
Mm-hmm. Is it possible to have a situation where it's like the opposite and you're like looking down a group?
Sure. You know, you could be asked the question, well, what about a carbon, fluorine, carbon, chlorine, carbon? So here, we'll do this down here.
Like
What if we had a
fluorine,
carbon,
bromine,
fluorine, carbon,
iodine.
fluorine, carbon, bromine, and carbon, iodine? So here, if we make the carbons all the same size, we already know a carbon fluorine looks like this, right? What's a chlorine going to be compared to a fluorine?
Bigger?
Yeah. So what's a bromine going to be compared to a chlorine?
Bigger?
And then what's a iodine compared to a bromine?
Bigger?
And these do get bigger like that. They get really bigger. So is it clear that this bond length is bigger than this one?
Mm-hmm.
And that one is bigger than this one?
Yeah.
And then finally, this one is the smallest. It's so small that I want to use like a high voice. It's very small, right?
If they
It's small.
spoke.
Then it gets bigger, and then it gets bigger, and then it gets bigger. Okay, the world would be a very different place if for bigger we used a high voice and for smaller we used a big voice, because this doesn't sound right, right? This one's smaller.
This one's bigger. You have to say this one's bigger.
This one's smaller. This one's even smaller. And this is the smallest. Doesn't fit.
Yeah.
Okay. It's weird how our minds work. Because you don't, depth of voice should have nothing to do with bigger or smaller, except for maybe that tinier people have.
So we could typically get a question like that for basically any combination of, doesn't necessarily have to be in the same group or in the same period.
No, but it should be the same atom with
Mhm.
other atoms. So
Okay.
it's kind of hard to do a carbon, nitrogen versus a oxygen, chlorine, and things like that. Although some of those you can do. Like what would you expect? A carbon, carbon, nitrogen, nitrogen, or oxygen, oxygen? Which one would you expect to be shorter?
The oxygen.
Right, because the oxygens are smaller. Right? So this should be shorter. Fair
Okay.
enough?
Yeah.
You should be able to answer these questions too. Which one's going to be the shortest?
The triple bond.
Yeah, exactly.
Okay.
Because it's pulling the atoms together. Here, it's kind of hard to draw what's going on because it's almost like you want to do this. If these are two oxygens, like here you got to do something like this, where you kind of make them overlap better because you don't want to really draw the atoms smaller. So they're being pulled together tighter.
Right. Okay.
So the book doesn't ask any questions like this to make any drawings like this one, but it would be hard to draw these to show why they get smaller using radii. Okay, so that's number 3. Let's look at number 4 now. Draw resonance structures for the sulfur dioxide molecule and determine the formal charges on sulfur and oxygen. Identify the best and briefly justify. Are the sulfur oxygen bonds polar? And is the molecule as a whole polar? If so, what is the direction of the net dipole in SO2? Draw the correct symbol next to each resonance structure. And is your prediction confirmed by the electrostatic potential surface, which is shown below? Okay, so I'm going to do a change share to number 4. So for number 4, we have to first draw the Lewis structure. And we have a total of 6 plus 2 times 6 for 18 electrons. We're going to put sulfur in the middle because it can make more bonds and it's less electronegative. Lone pairs on the oxygens until you get 8 on each. We've used a total of 16, so we're going to put 2 more here. Sulfur doesn't have an octet, so what we're going to do is make a double bond to sulfur so that it does have an octet. And then we're going to take a look at this. So we're going to say, okay, formal charge is 0, formal charge of -1, and formal charge of +1. And we wonder whether or not we can get a 0 on sulfur. And so if we make a double bond to this oxygen, not only do we get a formal charge of 0 on this sulfur, but we also get one on this oxygen. So you could argue that these two are resonance structures, but we don't give a hoot about this one because these are all zeros. So the nice thing about this problem is we don't have resonance structures. We only have one. Okay, so now when we look at this guy.
Those are my favorite.
Yeah, only have one. We notice that.
At least now, because I'm still learning.
Okay, so here, can you see how there are 3 pair?
Yeah.
So the best way to orient these is in a propeller-like shape. I call it a propeller-like shape because it reminds me of those old planes with a 3-prop propeller. So we call this trigonal or trigonal planar. Actually, I should say we call this trigonal planar. And these are 120 degrees. What do we call this where one of the pairs is a lone pair? We call this bent. But the angles are still about 120 degrees. Okay, now for bond polarity, the way you demonstrate bond polarity is you use these symbols that are like this. This is delta plus or delta positive, delta negative or delta minus. And you put the delta minus on the more electronegative atom of a bond. And when I say a bond, it could be a single bond, a double bond, or a triple bond. You do not use these symbols for lone pairs. So we have a bond here between sulfur and oxygen, and I've covered the other one up on purpose. We can decide the bond polarity here on this sulfur and this oxygen. And oxygen is the second most electronegative atom, so we're definitely going to put the delta negative on this oxygen. And we're going to put the delta positive here on this sulfur. And now if I cover up this bond, we can do the same thing for this bond. Which one's going to be delta negative? This one, because oxygen's more electronegative. And we already have a delta positive up there, so I'm just going to leave that like that. So these show the bond polarities. Now I'm going to draw this one more time. And I'm going to put this delta positive here, delta negative here, delta negative here. And what I want to show you is that if this is the molecule right here, we can actually cut it in half, and one side has a positive, one side has a negative. And the thing we want to do is see if this is possible. I mean, I could cut it right down the middle and say, okay, this side's negative, and you don't have a positive side and a negative side. The point is to see if it is possible to cut it in half and have a negative and a positive side. And we do. Since we do, we want to draw in the molecular polarity. So these here symbols are for bond polarity. For molecular polarity, you use an arrow with a plus sign at the end. I say the plus sign is at the tail of the feather, or the arrow. So you want to put the plus sign on the slightly positive side, and the arrow points towards the slightly negative side. And that arrow should be perpendicular to the line cutting it in two. So this shows you how to get to that arrow. And this is essentially what you want to show on an exam is this. You don't need to show all this. Now, likewise with this molecule here, if I had drawn it this way, in what direction would the arrow point for this molecule at the bottom?
The opposite?
Right, because the arrow always points to the more electronegative side. But another way to think about it is the plus side. Do you see how that looks like a plus sign on the bottom? The plus sign goes on the electropositive side, or the less electronegative side. So the way you draw the arrow compared to the molecule matters. You know, the arrow should match the molecule. So let me go back to number 4 and make sure that we captured all of the parts. I think there's one part we didn't capture.
A quick question, Tony. Are we only supposed to memorize the electronegative values of are we supposed to memorize all the electronegative values, just the ones on period 1, or I mean period 2, or are we just supposed to have a general idea of like the trend?
You should know all the ones in period 2 in hydrogen.
Okay.
In period 2, it's real easy because it starts with fluorine, which is a 4O. And then next to fluorine is oxygen, which is a 3,5. And next to oxygen is nitrogen, which is a 3O. It goes down by halves, right?
Yeah, for some reason beryllium in the chart in the textbook says 1.6, but I feel like that's not that important, right? Because it's kind of
No, do
negligible.
1,5. I have other books that say 1,5.
Okay.
And then hydrogen is 2,1.
Okay.
So know those and then know the trends. And the trends are, well, if you're looking at phosphorus versus chlorine, they're both in the same period. Chlorine is more electronegative because it's to the right. And if you have nitrogen versus phosphorus, they're both in the same group. Nitrogen is more electronegative. Okay? So if they're in the same period, you should know or be able to figure it out, which one's more electronegative is what I should say. And
Right.
if they're in the same group, you should be able to figure it out, which one is more electronegative without any numbers.
Right.
Okay?
Yeah.
Because it's too hard to memorize all those negativity values. I mean, no one does that. So if we go to the last question here, it says, is your prediction confirmed by the electrostatic potential surface? For this here, the little caption below says it's increasing in electron density from violet to red. So can you see that the top of this molecule, actually violet to red. So the top of the molecule is more violet-y, if you will, indigo blue. And where the outsides of the oxygens are, that's where it's red. Are you with me there?
Yeah.
So it says increasing in electron density from violet to red. That means it's more dense around the red. So if you have more electrons around the red, that means it's going to be slightly negative. So can we cut this molecule in two with a horizontal line and get most of the blue on above the line and most of the red below?
Yes.
So that means that this is polar. So it does match what we have, because in this case, we put the plus by the sulfur side pointing towards the oxygen side. Fair enough?
Yeah.
Now notice here that the bonds that they show, they're just bonds. They're not double bonds or single bonds. They also don't show lone pairs. So in this case, those sticks between the atoms are just to show you that they're bonded together without regard to whether it's a double bond, triple bond, or single bond.
Right.
However, the way this is drawn, is it obvious that those two bonds are the same length? They look the same, don't they?
Could be, yeah.
I mean, if one's longer than the other, it's pretty easy to tell.
Yeah.
So they look like they're the same length. And look at our structure. We have a double bond on the left and a double bond on the right, and they're both between a sulfur and an oxygen. Should they be about the same length?
Mm-hmm.
And they are. So I really like our resonant or our Lewis structure and our molecular structure.
Okay.
Okay.
I'll be right back.
Okay. Well, I'll go ahead and pause this. You let me know when you're back.
Yeah. Like.
Okay, so we're on to number 5, which has the greater oxygen, nitrogen, oxygen bond angle, NO2 -1 or NO2 +1. And then it goes on to say that the nitrogen oxygen bond length in one of these is 110, and then the other it's 124. So that means whether it's to the left or the right, it's 110 or 124, and which corresponds with which. So we've got NO2 minus, NO2 plus. One of these is 110 picometers and one is 124 picometers. So I'm going to do my change share. And let's take a look at how we would answer this. This is number 5. So to figure out the bond lengths and so forth and so on relative to one another, we want the Lewis structures. And we also need to decide which has the bigger angle or which one has the smaller angle, which means we need a 3-dimensional drawing or molecular geometry. So this one we have 5 electrons plus 2 times 6 plus 1 for the charge. So that comes out to 18 electrons. For this one, we have 5 plus 2 times 6 minus 1 for the charge. Because here, if we only had 17 electrons, it'd be neutral. To make it positively charged, we have to take away one of those electrons. So here we're looking at 16 electrons. All right, so let's do the NO2 minus first. (16 electrons, 17, 18. And for this one, we're going to draw 2 structures. And this is not a trick question. This is a real question here. Why do I not draw a double bond between this oxygen and this nitrogen in addition to the double bond here?
Because I could change the formal charges.
No, because you can't have more than 8 electrons on a second period element. So you cannot do this.
1, 2, 3. Right, the nitrogen would have
10.
Would have extra.
And you can't have more than 8 in the second period.
Yeah.
Okay, so there is another structure, and it looks like this, where we don't draw an additional double bond, but we have the double bond to the other side. So these are the 2 structures, right? Now I'm going to go ahead and white out this because I want to use that space. Okay, so how many pairs are on this nitrogen? 1, 2, 3. So I'm going to draw this guy so it looks like this. And I'm going to draw this guy so it looks like this. So we call this shape here bent. And because it's got 3 pair, what are the angles? So what are the angles when you have something like that?
I think it's 120.
It is 120. So I'm going to ask you for this one, what are the angles?
Same.
Okay, a little more conviction.
Same. Just kidding.
That's more conviction. All right.
120.
So let's take a look at the NO2 plus. We're going to start off with the same thing. Only this time we're not going to put any electrons on nitrogen as lone pairs. See these 2 here? We don't have them here. Because we only have 16 electrons. So I think it's pretty clear that we're going to have to do this to get the structure we want. Fair enough?
Yes.
Now, why don't I do this? Because this still has octets all around. Why do I do this on the bottom and not this on the top? And the answer is the following. Here we'd have a -1, here we'd have a +1, and here we'd have a +1. What do we have going on here? We have a 0, and a +1. So which structure is better based on formal charges?
The double bond on the
The two
end.
double bonds, because we only have one
Yeah.
non-zero formal charge. Now, why did I not bother with formal charges down here? Because I needed my octets. But if we did assign formal charges, they would be 0, 0, and -1, or 0, 0, and -1. And that's pretty good. I mean, I'm going to be honest with you. If you have a charge out here, you have to have a non-zero formal charge, because the
Okay.
formal charges add up to that number there.
Right.
So that means you're going to have at least a -1 somewhere. And here, when you have a +1, you're going to have a +1 formal charge somewhere, which we do. It's only when you have no charge that you might possibly have all zeros. So remember how you said, oh, I like those structures that are all zeros? Keep that in mind. Sometimes they cannot be all zeros. Fair enough?
Yeah.
Okay, and these are cases where they can't be all zeros. Okay, so here, how many pairs on that nitrogen?
So we got 2.
2. And that's the way you're going to draw it, right?
Yeah.
So it turns out that our Lewis structure is actually also the 3-dimensional structure, isn't it? And that happens sometimes. What do we call this shape, and what are the angles?
Linear.
Excellent.
180 degrees.
180. Okay. So if I go back and look at the question was, which has the greater bond angle? Well, NO2 plus has the greater bond angle. Agreed?
Yeah.
And then it also asks, which corresponds to which length? One of these is 110 and one's 124, right? So here, what is the bond order here when you average the two structures?
Nitrogen bond in one of these is 110. Oh, you mean the bond order? It would
The
just
bond
be
order.
2 divided. Wait. Yeah. Wait.
1.5.
Yeah, 1.5. Yeah.
How about here?
The same.
Yeah. Now, see, the reason I'm writing this right here on the left is because this molecule and this molecule are the same darn molecule, just drawn 2 different ways.
Right.
So
it's
this
just 3
oxygen
divided by 2, right?
Yeah.
Because you take the 3 total bonds,
So
and then
3 bonds divided by 2 structures is 1.5.
right.
Now here, what's the bond order? Do we have a resonance structure to average this with?
No, so it's just 2.
So the bond order is 2. And what's the bond order here?
Also 2.
Yeah. Now, this is one of the things that students always have trouble with when you start dealing with resonance structures, is they say, okay, I average these, I average these. Well, what if there is no resonance structure? Is it as easy as looking at it and saying a single bond is a bond order of 1, a double is a bond order of 2, and a triple is a bond order of 3? Yes, it is. So here, that's a BO of 2, that's a BO of 2, done. And our book doesn't spend a whole lot of time on that because they think it is so obvious. But they don't understand that this makes the topic confusing when you start looking at resonance.
Yeah, I think that is what makes it confusing. I guess in my head, the way I was doing it was a little bit different. I was just taking the number of bonds in one structure and dividing it by the number of like.
That's the way our book does it, and that's wrong.
Oh, okay.
That is wrong.
So
Because
you
you might
take
have
the
something-
total amount of both structures and then divided by.
Yeah, that's wrong. You look at all the structures.
How are you doing it? Yeah.
I look at all the structures that are okay, and I find the same two atoms, and I ask, well, what is the total number of bonds and how many structures are there?
The total number of bonds
Yeah,
is
so
6.
one bond there, correct?
Uh-huh.
How many bonds there?
2.
Two. What's 1 plus 2?
Oh, okay, okay. I see what you're doing. You're taking it from that structure and then the other structure, and
That's
then
right.
oh, okay, okay,
That's
got
the
it,
way
got
you're
it.
supposed to do it. Let me show you what our book does, and I really don't like it.
I think I was doing it the other way.
So our book says for this guy here, you got 2 plus 1 plus 1 divided by 3 bonds. So it's 4/3.
That's exactly how I was doing it.
The real way you're supposed to do it is this way. So your book does a shortcut, and it works a lot of the times, but sometimes it doesn't.
So we really should be looking at each of those individually, comparing it with the other resonance structure.
Absolutely. The same way I've been teaching it
Okay.
in lecture and in Q&A. And so here, this is a 2, this is a 1, and this is a 1 divided by 3 structures, which is 4/3. That's how you get that bond order right here.
Hmm.
And let me give you an example. There's this molecule called thiocyanate. And it's got 6 plus 4 plus 5 plus 1 electrons for a total of 16 electrons. So it turns out that there's a couple of good resonance structures. One of them is this. Another one is this. So these are pretty decent resonance structures for each of these. Okay, so here, what's the bond order for this carbon sulfur? Well, if you look just at this, you'd say the bond order is 2, because 3 and 1 is 4, divided by 2 is 2, right? And it's not. The bond order is 1.5. Why? Because it's a 2 and a 1 divided by 2. And what's this bond order when you average it?
It would just be 2, yeah.
How
Oh,
about
I
this one?
mean, oh, wait, I'm sorry. What is that one? Is just 6 divided by 2, yeah. Hmm.
Not 6.
Wait, 5. 5 divided by 2.
So 2.5, right?
Yeah. Sorry,
Okay.
my
So
eyes were deceiving me.
yeah, if you do it the way the book does it, what do?
Yeah, it would
You
give you
say, well,
2
it's a
instead of,
2.
yeah.
It's a 2 here, right? And what's it here?
Yeah.
It's a 2. Wrong.
Yeah, that's true.
So I teach it to you the way you should be taught it.
Mhm.
Some books don't look at this part, and they just focus on where all the resonance structures look pretty much identical.
Yeah,
And that's
probably
the
because we
reason,
were,
yeah, that's the reason they can get away with it. But I expect you guys to know a little bit more.
yeah, probably because we're just learning it, so they don't think we're gonna be
Yeah, but
into
this is
the
your second time
details.
around.
Yeah,
I mean, this isn't high school, it's college.
I know. Some of us didn't learn it that well last time around.
No, but you did learn something, and it's easier for you to learn new material.
We hope
Keep saying
so.
that to yourself.
Okay. Yeah, yeah. Be
Okay,
more
so let's take a
positive.
look at the share. We're going to go back here. So we've answered number 5.
Mhm.
We haven't. Which bond length corresponds to which ion? We never did answer that. So let me change my share again so that we can take a look at what we've done. So one of these is 124 and one's a 110. Here, the bond order is 1.5. Here, the bond order is 2. So which number corresponds with which?
Yeah, so the smaller one will correspond with the smaller bond order.
So you think 110 goes with 110 or 1.5, 124 goes with 2?
Right, because it's just the length.
It's the length, but what can we say about bond order and length? What's going to have a longer length? Large bond order or small bond order?
So the larger bond order, okay, yeah, when you say it that way, the larger bond order has a shorter length.
So this one should be shorter
Yeah, I think I reversed it in my head.
and this one should be longer. So this one should be the 110 and this one should be the 124.
Yeah, I
Okay,
knew
so you
that.
kind of,
I think I just got it mixed up in my head.
yeah, you just went with smaller, smaller, bigger, bigger. Kind of like your paycheck gets bigger if you work more hours. For most people. If you're a bartender, I think your paycheck gets bigger during happy hour. Although I may be wrong, maybe during happy hour they don't tip as well. I don't know. I don't go to bars, so I have no idea what that's like. Okay.
Right, Tony.
Oh, I haven't had a drink in like 25 years. Because
Yeah.
I used to drink a lot in college. That's what everyone does. But I'm allergic to alcohol. I turn bright red.
Oh, me too.
And
Like
so,
alcohol doesn't metabolize well with me, so I don't
yeah.
really.
And I got to the point in college where I could handle my liquor and I'd still be beaming red, but it felt so uncomfortable. I just,
One day you realize it's not worth it.
yeah, it's not worth it. I mean, turns out I can act stupid without alcohol.
I know that's how I feel. I don't really need that to like. Some people
Act
need
stupid.
that as like a way of being able to socialize with others.
Yeah.
Others don't.
Yeah, I perfected the acting stupid without alcohol.
Or just not caring without alcohol.
Pretty much. Okay, let's look at number 6. The formula for nitrile chloride is ClNO2-, and here they tell us directly nitrogen is the central atom. So I'm going to write down, we want to get the Lewis. We want to get the NO bond order. We want to describe the electron pair geometry and give angles. So describe means name it. And Fred is the wrong answer. Describe and draw the molecular geometry. That means name it. So I'm writing down little notes to myself of all the things I need to do. What is the most polar bond? We haven't talked about that, so I'll tell you how to figure that out. And indicate polarity next to the molecular geometry. So I'm going to say molecular polarity. So this is pretty much the whole chapter all in one problem. Okay. The only thing this doesn't really include is bond length and bond strength. But this is pretty much the whole chapter in one problem.
Do you think the homework is pretty comprehensive of like what the material we have to know for the exam?
I try to make it that way.
Okay.
I try to make the homework challenging because you know the exam is challenging.
Yeah.
Okay, so I'm going to change my share. And so here we go. We're going to have 7 plus 5 plus 2 times 6 electrons. So that's 24 electrons if I've counted correctly, because 7 and 5 is 12. 2 times 6 is 12, and 12 plus 12 is 24. I'm going to put nitrogen in the middle. I'm going to put chlorine on top so that it looks symmetrical. Just a little thing I like. Lone pairs on the oxygens first because they're more electronegative than the chlorines. And that's 24 electrons. So I'm actually going to have two structures that I want to look at. One is going to be this, and the other one is going to have the double bond to the other oxygen. Okay, so what is the NO bond order here?
1.5.
1.5. Now, what is the NO bond order here?
It is also 1.5.
Okay, so we can use the same answer for both bond orders. They're all 1.5 for nitrogen, oxygen, right?
Right.
Okay, electron pair geometry and angles, draw and name it. For these next parts, we only need to do it for one resonance structure because they will be identical. So here, if we draw the electron pair geometry, wouldn't you agree it looks kind of like that? And this one looks kind of like that?
Correct.
So they're identical, wouldn't you agree?
Correct.
So what do we call this electron pair geometry? Trigonal,
Pyramidal.
planar.
Oh wait, planars. Planar, yeah.
This one's flat. And what are the angles?
I think it would be, yeah, it's 120.
120.
This one, yeah.
Now, if we draw the molecular geometry, is it going to look pretty much like this?
Yeah.
And what are we going to call this guy?
Oh yeah, it's completely flat. So yeah, we would call it.
So we have to name it, draw it, and give the angles.
So that's not the name. Trigonal planar
Yeah, that's the name for this one. But how about this one?
for the molecular geometry. Oh,
Yeah. It's trigonal planar.
Oh, that's what I thought. Oh, okay.
They're both trigonal planar.
I'm getting you're confusing me.
Well, if it were this, lone pair on top, this would be bent.
Right. So, oh, okay, you're basically stating that in for the molecular geometry, we have to keep in mind like the lone pairs and
Right.
etc. because that changes the shape of it.
Right. So if we take a look at this guy here, that is the electron pair geometry, trigonal planar 120, right? But here, this is called bent, but it's still 120.
Right. So
Bond
the
angles
degrees
don't change, but the name
Yeah.
does if you have a lone pair.
Yeah, because the shape of it changes a little bit.
Correct. Okay, so here, which is the most polar bond? To decide which is the most polar bond, you look at electronegativities. So here's fluorine, 4O. What's oxygen?
So, oh, which is the most polar bond? You mean between those three, right?
Yeah, so what's oxygen for electronegativity?
Oxygen is more electronegative, and it is, I have
It's
not
less.
memorized
It's
it.
3.5.
The nitrogen?
Oh, we're comparing it to fluorine.
Oh,
Nitrogen is a 3O.
I thought we were comparing it to nitrogen.
Yeah.
Oh,
Now, I will tell you that for chlorine, it's not as electronegative as oxygen. It's less electronegative than oxygen. So pick a number that's less than oxygen.
2.5.
2 point, that's too low. How about 3O?
Yeah.
Okay, so what's your most polar bond? If nitrogen's a 3O and chlorine's a 3O, this is a non-polar bond, right? And here, this one's going to be slightly negative and slightly positive because oxygen's more electronegative, right?
Mm-hmm.
And here, this will be slightly negative and this slightly positive because oxygen's more electronegative. So the deal is since these guys are so close, it's pretty much a non-polar bond. Since these guys are different, it's a polar bond. So your most polar bond is the nitrogen-oxygen bond.
Right. And I thought it would be the wouldn't it be, oh, I don't know, does it make a difference if it's a double
No, because
single
remember,
bond?
it's not a double bond. It's a bond and a half.
Oh yeah, they're the same, right? Yeah, I guess just visually seeing it like that triggers me thinking like, oh,
If you wanted to draw it so it looked like a bond and a half, this is what you would draw.
right. Yeah, you have
Let's
gone
see.
over that.
You draw one electron there, so they're both a bond and a half.
That's
And
true.
the weird thing is you'd also have to put one out here and one out here to make it all work out.
Mhm.
And that's just wrong in so many different ways. Okay,
Right.
so does it have a molecular polarity? And I would say yes. Can you
Mhm.
see how the negatives are on the bottom half here?
Yeah.
So you would do this. The arrow always points to the more electronegative side.
Okay.
So number 6 is pretty comprehensive.
Mhm. Yeah.
What's the bond order here? Well, we have to average it. So what is it?
Just one.
Yeah. Okay. All right. Do you want to keep going or do you want to call it quits here?
We can keep going if you have time, or if
I do
not,
have
I can.
time.
Yeah.
It'd be kind of nice just to do this all.
Yeah, I would
And
like
then
to get all of it done just so I know I have a
that way
better
I can
idea of what I'm
post it instead
doing.
of coming up with a key.
Yeah, I'm fine with that. I'll just be quiet.
No, you have to answer questions when I ask. So the molecular picture below is epinephrine, a compound used as a bronchodilator and a anti-glaucoma agent. Okay, so here we're supposed to give the value for each of the indicated bond angles. So what I'm going to do is I'm going to draw what we see for each of those bond angles. So there's one.
Mm-hmm.
There's two. And you'll notice when I draw these, I'm drawing the central atom because we really want to see what's going on with the central atom. I don't want to draw the whole thing out, so that's why I'm just drawing pieces of it.
So for these angles, we're looking at like you said, the central atom, and that's where we're getting the angle from, right? In relation to
Exactly.
that central atom. That's the key.
So we're supposed to give values for the bond angles. And what is the most polar bond in the molecule? Okay.
Yeah, that seems pretty straightforward because you just have to look at what is attached to that central atom.
Right. So let's take a look here. And what are the bond angles here?
That's a 180 because it's
Nope.
a,
Nope.
oh, see, it's tricky.
Four pair, right?
Yeah, so it's actually a, what is it?
109.5.
Yeah, because the tetrahedral.
Right. What are the bond angles here?
This one is 120.
Three pair, so it's 120. How about here?
That one's also 120 because it's also a, what is it?
Yeah. So the tricky part is count the pairs. How many pairs
Trigonal
for number
planar.
4?
So there are 4 4 pairs there, so it would also be 109.5.
That's right. How many pairs here on this carbon?
It also has 4 pairs,
So the angles are?
109.5. That's
Okay,
a tricky one because it looks like a 90-degree angle.
right. But the drawing that we saw was not a molecular drawing. It was a Lewis drawing. And
Mhm.
Lewis drawings don't always show you the angles, do they?
They don't, but yeah, that's why you have to know it's a tetrahedral.
And the big thing that cries out, I'm a Lewis, is when you see something like this. 4 things attached and it looks linear.
Yeah, that one was tricky.
That one screams out, I'm not a molecular drawing. Okay?
Yeah.
All right. Now, what's the most polar bond? Well, if we look at the oxygens in this molecule, or the atoms in this molecule, this is a 3O, this is a 2, oh, excuse me. My bad. I always have to start at fluorine, otherwise I screw up. Fluorine is 4, 3, 5, 3, 2, 5, and hydrogen's a 2, 1. So the most polar bond is going to be the biggest differences between these values. So can you see that the best that we can do is probably a fluorine hydrogen? And if we look at the molecule, there are no fluorines, so it can't be that. So the next best is going to be an oxygen hydrogen, right? Because the difference is the greatest.
Yeah.
So that is going to be the most polar bond. Any oxygen hydrogen bond will be the most polar. Most polar because the biggest difference in electronegativity. And that's how you do it. Biggest difference, most polar.
Okay.
That's straightforward. Okay, so if we go back and look at the molecule, you can see there are no fluorines there, right?
Yeah, so
Now, I'm going to stop you for a moment before you ask your question, because I do want to point out to you that in the very top drawing where you see the HOC and it looks linear, look in the bottom one at the same angle where they're trying to show you angles.
yeah, I just noticed that. Yeah.
Now, they don't show the lone pairs, so it's hard to tell if that's 109.5 or 120.
Yeah, but it's definitely a hint.
It's a hint. Okay, but we didn't need that hint. So I interrupted your question. Do you remember what it was?
No, I think I actually figured it out
Okay, good.
because I was just gonna ask about the polar bond, but it's for the whole molecule, not for like parts of it, obviously.
Yeah, it just asks which is the most polar bond.
Yeah.
And if we look at this molecule, does it look like it might be polar? And it's, it's a tough call because you could cut it and have 2 of the oxygens on one side and say it's kind of polar, but this is kind of a non-polar molecule.
Okay.
Okay. So number 8, methyl acetamide, which has this formula here, is a small molecule with an amide link, which is a carbon to nitrogen bond. So do you see the CH3 in the formula where it says CH3CO?
Yeah.
Okay. So now look at the structure below. Do you see the first gray sphere on the left? That's the carbon. Do you see the 3 white spheres attached to it?
Yeah.
Those are the hydrogens, CH3. Do you see the next gray sphere to the right of the first one? That's a carbon again.
Okay.
And you see the 2 lines going to a red sphere. The red sphere is an oxygen. So do you see in the formula above where it says CO? That is the CO below where you have a C double bonded to an O. Now, in the formula above, do you see that you have a nitrogen after the O?
Yeah.
So looking at the formula, you might think, oh, okay, that nitrogen is bonded to the oxygen, but it is not. It is bonded to the carbon.
Hmm.
And we know this by looking at the structure below. We can see that that carbon, which is double bonded to the oxygen, is also singly bonded to the nitrogen. Do you see that? The nitrogen is a blue sphere.
Yeah. Mm-hmm.
And then you'll notice that the nitrogen is bonded to a hydrogen. And then the nitrogen is also bonded to a carbon, which is bonded to 3 hydrogens, kind of another CH3, if you will.
Mm-hmm.
Now, you might ask, so if that's the 3-dimensional drawing, does everything have an octet? And the hydrogens have a bond, which is what they want. That's 2 electrons. Each carbon is surrounded by 4 bonds, so that's 8 electrons. The oxygen only has 2 bonds, which is 4 electrons, right?
Mm-hmm.
The red oxygen, 2 bonds, 4 electrons.
Mm-hmm.
It should have an octet. So what do we not see in the molecular drawing?
We don't see the lone pairs.
Correct. And how many are on oxygen?
We should have a total of 8, so it would be 4.
4
I mean,
electrons
2
that are
lone
not
pairs.
bonded.
Yeah.
2 lone
Lone
pairs. You
pairs.
got it. You got it. What about the nitrogen? We don't see 8 there. So what's going on?
Yeah. So the nitrogen. Let's see. The nitrogen. Yeah, it should also have 8, right? So it would be. It must be missing a pair.
That's right.
It must have a pair somewhere.
That's
Probably
right.
at the top.
So that's how we kind of figure these things out. So here is the molecule polar. And this one, I want you to imagine a horizontal line where you have the red sphere on top and the blue sphere on the bottom. Okay. That is a way to get the most electronegative atom on one side, correct?
Mm-hmm.
However, oxygen is a 3,5, nitrogen's a 3,0. Are they that different in electronegativity?
Oxygen and nitrogen.
Yeah, 3,5 versus 3,0. And the answer is,
No.
if they're only half apart, that's not a big difference.
Okay.
So what we would really want to do for this molecule is if we could chop it in half some way and get both the oxygen and the nitrogen on the same side. Can we do that?
I don't think so.
Okay, so this is pretty much nonpolar.
Okay.
So we would say, is this molecule polar? You'd say no, because we don't have them. We can't get the most electronegative atoms on one side of the molecule.
Okay.
Okay, where do you expect the positive and negative charges to lie in this molecule? So here, let's take a look. Do you remember that the red is more negative? So here we say that, okay, based on this, the electrostatic potential, the negative does lie more on the oxygen.
Mm-hmm.
Okay.
Mm-hmm.
But the other thing we could say is if you look around this blue one here, it's a lot of green, which means it's also kind of negative. So if you look at the electrostatic molecule, you could say, well, based on the electrostatic molecule, we do have a concentration of negative on one side, so we could call it kind of polar. So for number 8, if we look at the drawing, and this is the ball and stick model that I'm drawing now. Let's see, what am I going to do here? I guess I'm going to do this.
Are you saying that if you maybe rotate it a little bit, you might be able to cut it in half?
Yeah, you could. So here, this is the molecule drawn with what I call the ball and stick model. where the symbols are balls and the wedges and dashes and lines are sticks. So this is pretty much the three-dimensional orientation of it. Turns out you can actually draw it like this. This is really beyond the scope of our class, to be honest. So do you see this CH3 that I'm pointing at here?
Yeah.
That's it right here.
Hmm. Mm-hmm.
And you see this hydrogen here that I'm pointing at?
Yep.
That's it right here. And then there's a lone pair here. So here we could kind of say slightly negative, slightly positive.
I was thinking
guess,
of
you know,
rotating it 100%, like, or not 100%, like,
this is about the best you can rotate it. Now
like
for
90
this one,
degrees.
for this one, you can do this. So if you look at the electrostatic map, so I'm going to do a change share. So do you see the electrostatic map here with the red where the oxygen is?
Mm-hmm.
That means negative.
Yeah.
Now I'm going to do a change share. I'm hoping I resumed recording. Do you know if I did?
Yeah, it's recording.
Okay. So if I go back to here, do you see how we can just say, forget the nitrogen, let's just focus on the oxygen. We got the oxygen on one side, so it is slightly negative.
Yeah.
So I guess Tony's method does work. Just look for the most electronegative atom. If you can get it on one side, it's polar.
Okay.
Okay. We don't have to resort to this and manipulating it so that we definitely have the most electronegative ones on one side.
Yeah. In my head, I was thinking of just like cutting it in half, like between the oxygen and the nitrogen, and then just pointing the arrow towards the left.
You don't want to do that.
But I don't think that's right.
This just looks easier.
Yeah.
Okay. Because here you're only getting these two hydrogens here, where if you cut this up, then you got the carbons on both sides, they kind of even each other out and so forth and so on.
Mm-hmm. Okay.
So we don't want to do that because you're just putting too much on one side versus the other.
Okay.
And you do have the battle here. So I would go with, and number 8, we're answering this also based on the electrostatic map, which I'm going to show you again.
Right.
So it's based on more than just R splitting it in half. It's also the electrostatic map.
Okay.
Okay. Which clearly puts the red one on the top.
Yeah.
Okay. Okay. So number 9, acrylamide is a known neurotoxin and possible carcinogen. That means possible cancer-causing agent. It was a shock to all consumers of potato chips and French fries a few years ago when it was found to occur in those products. Oh my goodness. If you eat potato chips and French fries, you're eating acrylamide, which may cause cancer. Okay. Sketch the molecular structure of acrylamide and identify all bond angles. So this is a tough one. And I'm going to show you how you would figure out what's going on. So I'm writing the formula down right now. So we want to get the molecular structure. All bond angles. Which carbon-carbon bond is the shortest? Show the shorter carbon-carbon bond, which is going to be the double or the triple if there is one, right?
Yeah.
And is it polar or non-polar? And then we have the amount of acrylamide found in potato chips is 1.7 milligrams. per 1 kilogram of chips. Do you know what 1 kilogram of chips is in pounds?
That kind of seems like a lot of chips. It seems like more than like about 2.5 pounds of
Yeah,
chips.
that's a big bag of chips. And 1.7 milligrams means 1.7 thousandths of a gram.
Yeah, that's a lot.
And a gram is 1.1 milliliter about. So take that 1 milliliter of water and take 0.0017 of that. That's the amount of acrylamide. So it's supposed to be, you're supposed to think it's not much. So they say one serving is 28 grams. That's about 1 ounce. So if you eat an ounce of chips, how many moles of acrylamide are you consuming?
That's
And
a
what would make
lot.
this more interesting is how many molecules are you consuming? But
That's from the frying process.
yeah, it's from the frying process. Basically, fried foods create carcinogens. That's why when you drive through a McDonald's, a Wendy's, or any of those places, they tell you that the foods here contain cancer-causing agents or
Yeah.
carcinogens.
Yeah.
So it also happens if you, even if you're a vegetarian and you like to grill foods, you're making carcinogens.
Yeah, that's why I say it's better to have as much like raw and like not as like processed and
Yeah. If you want
cooked.
to, get rid of carcinogens, then you would eat raw food. The whole enzyme thing I don't buy because they say that when you eat raw foods, the enzymes in the foods help to break down the foods themselves.
The
But
enzymes in the food
yeah,
or in our
but,
stomach.
but the fact is that the enzymes in the food get broken down in your stomach.
Yeah, our stomach
So
does that for us.
yeah, so the enzymes are just protein.
Hmm.
But at any rate, but the other problem with eating raw is that, in my opinion, it just doesn't taste as good. I like a good char.
Yeah, yeah, I'm the
Like,
same. I like that
when you have your
smoky
carrot
taste.
and grill it and it's got some little black marks on it, it tastes so much better.
I know, I'm like that too, but you have to get used to kind of like introducing a bit more like raw and like not as fried or cooked foods because I do think that it's probably healthier.
I
Makes
think
sense.
it's a great idea for someone who's young, but for old dogs like myself, I'm going to go for the taste. All right. So I'm going to do a change share so that you can see what I am drawing. Now, here's a few things that I'm going to do. I'm going to point towards these carbons and these oxygens and these nitrogens. And the reason I'm pointing to those is because I know how many bonds they like to make. Carbon likes to make 4, oxygen 2, nitrogen 3, and hydrogens like to make 1, right?
Hmm.
So when I'm trying to figure this out, I'm thinking, okay, so this carbon needs 4 things bonded to it, or at least 4 bonds. Doesn't it make sense to do this? Have 1 hydrogen here and 1 there, and then the carbon for this part.
Hmm.
And then I have a double bond, and wham, I've got my 4 bonds to that carbon. Fair enough?
Hmm.
So these 2 carbons are bonded together. And then where are we going to put that hydrogen? I can put it bonded to this carbon, or I can put it bonded to this carbon here to the left. And I think I have room for it, so I'm going to just try it and put it there. So how many bonds do I have to this carbon now?
Bonds,
Yeah,
3.
3, and I want 4, right?
Hmm.
So I've used this hydrogen, and now I'm thinking, well, what if I bond it to that carbon? Well, that works out great.
Hmm.
Now, this is the little tricky one, and here's the trick. Whenever you see a CO, it should jump out at you and say, that's a double bond. So that's a little trick I'm giving to you.
Hmm.
If you see a CO, you should think double bond. Okay, so if that's oxygen is double bonded to that carbon, we know oxygen likes to make 2 bonds, so there's 2. We know carbon likes 4, so I see 3. So what's the next thing bonded to that carbon?
The nitrogen?
Right. And then naturally, where we're going to put those 2 hydrogens?
Probably like on each end.
Like on the nitrogen, right?
Yeah.
And nitrogen likes 3 bonds, and here it has it. Now, let's throw in the lone pairs. Does it make sense to have a lone pair there and 2 here?
Yeah.
Okay, let's find out if that's okay. How many electrons there that we can see?
There's 8.
Okay, so I'm going to cover those 8 up. How many there that we can see?
Also 8.
So 8 and 8 is 16. So I'm going to cover those up. How many here?
There's 12.
Okay,
Wait.
I'm going to agree there's 12. So we have 8, 8, and 12. What is that total?
16, 26, 28.
Okay, 28. And let's see how many electrons we should have. How many hydrogens do we have up here? 1, 2, 3, 4, 5. 5 hydrogens at 1 each is 5, right? How many carbons? 1, 2, 3. 3 carbons. And how many valence electrons per carbon?
4.
Okay. How many oxygens up here?
There's just 1 oxygen.
And how many nitrogens?
Just 1. So
How many valence electrons for it?
5.
Okay, so let's add these all up together. What do we get?
Is that 17 plus 23?
Okay, I'm going to show you a trick.
28?
Here's the trick. What's 5 plus 5?
10.
What's 12?
22 plus 6, 28.
Okay, so don't do it from left to right. Add the
I
numbers
know.
that are
I
easy.
always do it from left to right.
No, don't do that. You always add them up the easiest way you can.
Yeah.
So we said that there's 28, right? Looking at this.
Mm-hmm.
And just looking at the atoms, we said there should be 28. So it was okay to put the lone pairs there.
Mm-hmm.
Okay, let's draw the molecular structure. What are you going to draw this carbon as since it has 3 pair? Isn't it going to be a propeller?
Right.
So does that look like a propeller?
Mm-hmm.
How about this one? What's it going to be like?
The same.
A propeller, but here we're going to have to draw it like, instead of like this, we're going to have to draw it like this.
Because they have to be like separated from each other.
Right.
Like
So I'm
equally
going to do
distant.
this. I'm going to do the hydrogen down here and this carbon over here.
Mm-hmm.
What's this carbon supposed to look like? Also a propeller, right?
Yeah.
What's this nitrogen supposed to look like? Well, it's supposed to look like this. Okay.
Mm-hmm.
So what I'm going to do is I'm going to do this. And I'm going to do this. And then I'm going to put the lone pair there. Another way I could do this is this way. There's lots of different ways you can do this. But the way you really want to do it is so that when people look at it, they get an understanding of how things are arranged in 3 dimensions. What do you think of this? Can you see how this looks kind of like an upside down stool?
Yeah.
So either of these are fine for the 3-dimensional drawing. And with this one, we're supposed to say which is the shortest carbon-carbon bond, right? That's the shortest carbon to carbon bond. Agreed?
Mm-hmm.
Why is it the shortest?
because it's the only double bond.
Right. The bond order is 2. Bigger the
It
bond
has the
order,
highest bond order, yeah.
shorter the bond. Is this molecule polar? Well, this one I think we could definitely cut this way. And since carbon and oxygen, or nitrogen and oxygen are the most electronegative, we could do that. Or you could do this, and either would be fine. So we're going to say it's polar. Fair enough?
Yeah.
Okay, now, how many moles of acrylamide are in here? Well, we need the molar mass of this guy. 5 hydrogens is 5.05. 3 carbons is 36.03. 16.00 and 14.01. Add these all together, and do you see how 36 and 14 add up to 50?
Mm-hmm.
So that's 50.04. And then I'm going to say, or I could say 16 and 14 is 30, right? But what I'm doing is I'm doing this in my head and adding up the ones that add up to nicer numbers.
Right.
And then 5.05 and 16 is 21.05, right?
Mm-hmm.
And now I've got 71.09. So I'm going to put the last answer down here. We've got 28 grams of chips times 1 kilogram of chips per 1,000 gram of chips. Now, why am I using 1 kilogram of chips here? And the answer is because this conversion factor above tells me milligrams per kilogram, right? So
Oh,
now
yeah,
I'm
to say per kilogram. Mm-hmm.
yeah, 1.7 milligrams of acrylamide. I'm going to put A for acrylamide because I don't want to spell that out.
Yeah.
Per 1 kilogram of chips. And then times 1 gram of acrylamide per 1,000 milligrams of acrylamide to get rid of the milligrams. And then times 71.09 grams of acrylamide, upside down, 1 mole of acrylamide per 71.09 grams of acrylamide. And that'll give me moles of acrylamide. This is a hard one to estimate, wouldn't you agree? But one thing I can say about this number is it better come out to be smaller than 1. Agreed?
Mm-hmm.
Because I'm dividing by 1,000, dividing by 1,000, and dividing by 71.09. So this better turn out to be a lot smaller than 1.
Mm-hmm.
So we get 28 times 1.7 divided by 1,000, divided by 1,000, and divided by 71.09. So if I put this in scientific notation and use 2 zig figs, I get 6.7 times 10 to the minus 7 moles of acrylamide. So it doesn't seem like very much acrylamide, does it? In 1 serving of chips.
Yeah, I mean, I guess not.
Let's find out how many molecules. It wasn't asked, but let's figure out how many molecules. So we have 6.7 times 10 to the minus 7 moles.
Yeah, it's just hard to know in moles. Like, it have to be like in grams or something to know how much that is.
So we're going to multiply by 6.022 times 10 to the 23rd molecules per 1 mole. So it's 4.0 times 10 to the 17 molecules. And I think I read somewhere that you have like maybe 4.0 times 10 to the 10 cells in your body. Or maybe it's 10 to the 12. 10 to the 12 would be trillion. So you got 4 trillion cells in your body. I think that's too many, but let's just pretend that, right? That means that you have 10 to the 5 molecules per cell. 10 to the 5 is 10,000. So when you eat that 1 ounce of chips, every one of your cells is getting at least 10,000 acrylamide molecules. Does it sound like a lot?
Yeah, it does seem like quite a lot.
It is. When you take 1 aspirin, each one of your cells is getting like 10,000 aspirin molecules. Probably more than that. It's probably more like 100,000. But
Yeah.
what you're supposed to get is an appreciation for just how small molecules are and just how powerful medications can be.
Mm-hmm. And also, I do wonder why they sell really high dosages of like medicine sometimes, even if you
Right.
don't really need that much.
Well, sometimes you do because, when people take a biology class, right? And you look at a drawing of a cell and you see all the different things in there, the different structures. And then they show you a drawing of what those structures are made out of based on molecules. It is impossible to draw the cell so that you can see all the molecules because there's so many molecules in one cell.
Mm-hmm.
There are billions of molecules in one cell. Billions.
Mm-hmm.
So does that sound like a lot?
Yeah. That's
Yeah.
a lot of molecules.
So now if you have billions of molecules inside your one cell and you're adding another 10,000, that's not
That doesn't
much.
seem like a lot. Yeah, that's
No.
crazy.
That's like saying, you know what? I'd better trim my hair before I weigh myself because otherwise I'm going to weigh too much and I'll be fat, right?
Yeah.
So people don't get the sense of how many molecules are inside of a cell from a drawing in a biology book.
Or how our body is like a whole world of tiny things.
One cell. I mean, if you were a atom on a wall and you were inside a cell, that would be a huge world.
Yeah, that's crazy.
You would be, if you were an atom in the middle of the cell looking around, all of the other molecules in the cell would be like the stars in the sky. You'd say it's an endless number of molecules out there. That's how fantastic cells are. Oops, that made me sound like I like biology and stuff. Okay, we're almost done. So do you understand number 9?
Yeah, it wasn't as hard as I thought it was going to be.
Number 10, the equation for the combustion of gaseous methanol is as follows. Draw the Lewis structure of each molecule. So I'm going to write out CH3OH2 plus 3O2 gives you 2 CO2 plus 4 H2O. So what I'm having you do here is we're going to be using bond dissociation enthalpies to figure out how much energy this reaction gives off or absorbs. And we're going to use bond dissociation energies or that are in the book. So let's take a look here. We're supposed to estimate the heat of reaction using bond dissociation enthalpies, and then we're supposed to get the enthalpy of combustion for 1 mole of methanol using something that we learned in a previous chapter. So this is checking to see if 2 different methods give us pretty much the same answer. All right, so I'm going to switch screen. So can you see the reaction? We want to get
Yeah.
the enthalpy of reaction. So I'm going to put question mark. We want to do it based on bond energy and then based on enthalpies of formation. So two ways, A and B. So for A, to estimate it on bond energies, you need the Lewis structures, and you don't need a molecular structure, just a Lewis structure. So there's your Lewis structure of methanol. And here's your Lewis structure of oxygen. Here's your Lewis structure of carbon dioxide. And here's your Lewis structure of water. I had to put it up kind of at an angle because I was running out of room. Now, mind you, you've got 2 of these, 3 of these, 2 of these, and 4 of these. Now, when we talk about bond energy, if we want to break a bond, the bond energy is positive because this is endothermic. So before I move on, I want to make sure you understand that.
Yeah.
So as an example, I'm going to say, do you see this oxygen-oxygen double bond?
Yeah.
If we want to break that, we have to put energy in to make that happen. Does that make sense?
Mm-hmm.
Okay. Now, if you make a bond, the bond energy is negative and it's exothermic.
Right.
So if I take these 2 oxygen atoms apart and put energy in, if I let them come back together, it will release energy, the same amount.
Mm-hmm.
One way to draw that would be this, if we use an energy level diagram. So here's the energy of O2. And if I made it look like this, so to take these 2 atoms and split them apart, I have to put energy in. But what happens if I let them come back together? Energy gets released.
Mm-hmm.
Okay?
Okay.
So we can estimate the enthalpy of reaction by taking all of the bonds and find out what bonds you have to break. So positive, and this is called the bond dissociation energy.
Mm-hmm.
But I'm just going to say positive bonds breaking, because that's endothermic, right? And then minus the bonds that you make, because we know that's exothermic, so that's why I put the negative here. So if we take a look at all the bonds we're breaking, let's take a look at those. How many carbon-hydrogen bonds are we breaking in this molecule? Mind you, we have to break them all. So how many
Okay.
carbon-hydrogen bonds are we breaking?
1, 2, 3.
3 of them. But how many molecules are there?
2.
2. So how many are we really breaking? We're breaking 3 for 1 molecule.
6.
How many for 2? Right. So here we're going to say 6 carbon hydrogen single bonds, right?
Mm-hmm.
Okay. How many carbon oxygen bonds are we breaking in this molecule?
1.
1. But how many molecules are there?
2. Oh, I mean 2. Yeah.
So that's 2 carbon oxygen single bonds, right?
Mm-hmm.
How many oxygen hydrogen bonds are we breaking in this molecule?
1.
How many molecules total?
2.
So 2 oxygen-hydrogen bonds total. Agreed?
Mm-hmm.
How many oxygen-oxygen double bonds in this molecule?
2.
No. How many oxygen-oxygen double bonds in the molecule?
1.
1 double bond.
Mm-hmm.
How many molecules?
3.
So we're going to say 3 oxygen-oxygen double bonds. So those are all the bonds we need to break. And this is the amount of energy it's going to cost. How much energy is released? Well, take a look at this molecule here. How many carbon-oxygen double bonds in one molecule?
How many oxygen, carbon?
Carbon-oxygen double bonds.
Yeah, 2.
2. And since we have 2 molecules, how many is that total?
4.
So we're going to put 4 times carbon-oxygen double bonds. How many oxygen-hydrogen bonds in one molecule?
2.
2, but 4 molecules, how many total?
4.
So this is how we estimate the bond energy or the reaction for this. Now, no one memorizes these numbers. You just look them up in the book. So let me show you how to look them up in the book. And you're not going to let you be able to use your book on the test, but for a problem like this, I'll give you the numbers. I'll give you a chart. So what you want to do is be able to use a chart if given one. So we're looking for bond strength. So do you see this chart here that says bond dissociation enthalpies?
Mm-hmm.
That's bond strength. So the ones we want are carbon hydrogen. A carbon hydrogen, I'll show you right here. Here's hydrogen, here's carbon. It's 413 for a single bond. And that is kilojoules per mole. So we're going to write 413 kilojoules. Now, rather than show you each of these one by one, I'm just going to tell you that the carbon oxygen single bond is 358. The oxygen hydrogen single bond is 463. And this one I'm going to show you, the oxygen-oxygen double bond. Do you see it right here?
Yeah.
498. And then minus a carbon-oxygen double bond is 745. And a hydrogen-oxygen we already found out is 463. So now we just use our calculator. And if we wanted to estimate the answer, we would say something around 6 times that is 2,400. 2 times that is 700. 4 times that is going to be roughly 900. And 3 times that is going to be roughly 1,500. So we add it all up together and we get 24 plus, how do I want to do this? 24 plus 15 is 39. 39 plus 8 is 48, and 48 plus 7. So this is 55, roughly. So I'm going to figure out what that is off of my calculator. And I get 5,614 kilojoules. And my estimate was 5,500, so I'm pleased because I'm within 10%. Now minus What's 4 times 475? Well, 475 twice is going to be around 1,500. So that's going to be minus 3,000. And 8 times 463. I know that 463 and 463 is
You
around
switched
900.
the numbers around for it's 745 now, 475.
Oh, this one. Well, 4 times this should be around minus 3,000. Right?
Oh yeah, I thought you said 475. I
I
heard you
may
say.
have,
Oh, okay.
but in my mind, I multiplied it correctly.
Oh, that's so weird. Okay. Yeah, I could have sworn you said 475. Never mind.
Now I
But
know.
yeah, but then I saw the number. Yeah, it was.
Okay. Now 2 of these is going to be around 900, right? So 8 of them would be around 900 times 4, so 3,600. So this should add up to around 6,600 if I add it up correctly. So let's find out. 4 times 745 plus 8 times 463, and I get 6,684 kilojoules. And I estimated that, so I'm happy with that. Add these two together. And I get 1,070 kilojoules negative. So this basically says that if you combust methanol, you will release that much heat. Okay? Do you follow?
Yeah.
But that is for 2 moles of methanol. So this value would be 535 kilojoules per 1 mole of methanol. How do I know this is for 2 moles of methanol? Because of that, right?
Yeah, the equation.
Okay. Now we're supposed to figure this out based on enthalpies of formation. So here's what we do. We're going to write this again. And using enthalpies of formation, the reaction is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. Do you kind of remember that formula?
Yeah.
So here, if we look at the products, we've got CO2. So we're going to say 2 times the enthalpy of formation of CO2 plus 4 times the enthalpy of formation of H2O. And I think this is a liquid, then that matters. Minus 2 times the enthalpy of formation of CH3OH and 3 times the enthalpy of formation of O2. So when we look up these enthalpies of formation, we're supposed to use gas for this guy, gas for this guy, gas for this guy, and gas for this guy. We're doing it gas all the way around. So I have to use the appendix in the book for this. And these are numbers that you, again, would not memorize. You'd just be given them. So here we would have 2 times negative 201 kilojoules plus 3 times 0 kilojoules, because the enthalpy of formation of an element in its pure state is 0. CO2 is 2 times minus 393.509 kilojoules. And H2O in the gaseous state is like minus 285 or 245 or something. 241. Okay, so if I estimate this first part, that's minus 800. That's going to be minus 480 twice, so minus 900, minus 1,000. So minus 1,800-ish. That's going to be minus 400. But that becomes a positive. So my total will be a grand total of like minus 1,400. And that's just an estimate. Okay, let's see what we got. Okay, so this total is 1,803 kilojoules. Wait, I'm not sure if I did that right. It's 1,754 kilojoules minus, well, I can do that one in my head, right? Negative 402 kilojoules. Did I do that right?
Yeah, I think so.
So minus 402. So when I total these, I get 1,352 kilojoules negative. And that's for 2 moles. So if I divide that by 2, we come out to 676 kilojoules per mole. And when you look at these answers, they're not too far apart. So although the answers are slightly different for each, they tell us that both methods have some validity to them. And that also tells us that this formula here and this formula here, those two formulas, what does it tell us about those two formulas, if you had to guess?
They work very similarly.
Well, here's what I'd say. It tells us they're models.
Mm-hmm.
They help us to make a prediction as to what the actual amount of energy would be. And probably both of them are wrong for the actual amount of energy which you would want to measure. However, both of them are pretty close to one another for their values. And that's something I try to make a point of in my chemistry classes, is that every model we have is not the defining way that molecules behave, but rather the model is based on what we see. And the model is our best attempt, or maybe a better attempt as time goes on, of trying to say this is how things kind of behave. And why is it that we like models? And the answer is because they do give us some insight into how things behave. And why are we always trying to improve upon models? Is because we want better insight. And you can see that really in today, when you talk about COVID-19, you know, the first models that came out about how COVID-19 was going to spread and how it would affect the people, you start off with some very simple models where people were saying, this is what we think is going to happen. And what happens over time is you start fine tuning it. At first people were saying, don't wear masks because it's not really going to help. Some people were saying the size of a viral molecule or particle is so small it can get through any mask. And that's absolutely right. But it turns out that the viral molecules don't tend to spread by themselves. They spread in droplets. So do masks help stop droplets? Absolutely. And it turns out that mask wearing really stops the spread of coronavirus. And in fact, it stops the spread of a lot of different things, like, how many people are getting the flu these days.
If only you could go back in time.
Yeah. Well, you see, that's just it. You can't go back in time. You go forward in time, but you learn from the past.
Yeah.
So
But the
moving
funny
forward,
part is that we had a lot of this information from the other countries that were doing it. All of these other countries were wearing masks.
well, you know what? I lived in Japan and they wore masks all the time.
Yeah. They've
But
been doing it for a really long time too, like as like a hygienic thing, I feel like, because they know that you spread diseases more often when you're in close quarters and
right, well, Japanese people wear it because they care about other people, in my
yeah.
opinion. So if you're sick, you wear a mask. If you're not
Yeah.
sick, you don't.
Yeah, that makes so much sense, but I feel like I know like people here used to make fun of people who are like, they see them like wearing masks all the time, like, oh my God, they're so ultra hygienic, always wearing masks. And it's like,
But there's
okay,
kind
but
of,
it makes sense when you're in like a closed, like in airplanes and buses and things like that, and like you don't
but
want to spread things.
but before we say that we knew ahead of time, here's something else I think we need to understand is that when you're coming down with the flu, you know it. You feel fluey. You get chills. Uh, you get a headache or body aches. You know you're coming down with the flu or the cold, and so you wear a mask. One thing that's different about COVID-19 compared to the flu or the cold is that a lot of COVID-19 is asymptomatic. So how would you know to wear a mask? And so kind of the new thing to me is that, okay, a lot of it does spread asymptomatically. So with that in mind, everyone should wear masks as if they had it.
Yeah, exactly. You would have to be basically wearing a mask in really close, when you're in close proximity to other people, like in buses or airplanes.
Right, right. And even in Japan, before COVID-19, people who weren't sick didn't wear masks.
Hmm.
But now everyone is because you don't know if you're sick. That's the scary thing about COVID-19. And, the flip side of the coin is that a lot of people say, well, if most people get it and they don't feel anything, then why even bother wear masks? And the answer is to protect the 2% who might die.
I know. It's
So
really sad when you think about it that way.
if you care about grandma and grandpa, wear a mask. If you don't care about grandma and grandpa, then I probably don't like you.
I know it's tough. Are we starting with chapter 9 next week?
Yep, we're going to start next week with 9.
Okay.
You should take the quiz for this chapter, I think, by Monday.
Okay.
The exam for the 3 chapters is going to be Wednesday, but I'm going to go ahead and start with chapter 9. Chapter 9 PowerPoint presentations, lectures, and old Q&As have already been published.
Today?
Yeah, just did it today, this morning. And I also
Nice.
published chapter 10.
Wow.
Chapter 9, the lab, has been published. We're only going to do one lab for chapter 9. So
Mhm.
next week, there's only going to be one lab, not 2.
That's good.
And it'll be due the following week.
Okay, that's
And for
good.
chapter 10, there's only going to be one lab. And that'll be
That's
due the
good.
following week.
Okay.
So as we get towards the end here, we're going to be doing fewer labs because I know you have kind of more stuff to do. Plus, you're going to have a lab report that you're going to have to do. But I'm not going to assign that until after you take the exam so that you don't feel pressured. And when I assign
Don't
it,
feel pressured. I hope you don't feel pressured already. But
Well,
I was gonna ask.
you won't feel like you want to go out and scream somewhere.
I was gonna ask, is this exam number 3 is going to be our last exam, or are we gonna have another exam number 4 before the final?
There will be an exam 4. It'll be the last week of class. And when I say the last week, I mean the last normal week. And your final exam will be during finals week.
Okay. All right.
So exam 4 comes like around May 9th or something like that, or May 7th.
Okay.
And the final exam comes like May 13th or 14th, something like that.
Yeah, it was helpful when you like published everything really early for this section, because it kind of like triggers.
Right. Well, for the next section,
Yeah.
the first 2 out of 3 are published, except for one of the labs. I haven't published it yet.
Okay, that works. Thank you.
Yeah. I'll publish 23 later.
Yeah, that's fine. I guess I'll see if I see you on Monday. Just kidding.
Yeah, I mean, you should definitely show up on Monday, because Monday, the focus of these times are what questions you have. And if your questions are about the previous 3 chapters because you haven't looked at chapter 9, that's fine. I will do what the students want to do.
Okay, well, thank you, Tony. Thank you for your help, and this has been really helpful for me.
Yeah, and thank you, actually, because this means now I don't have to publish a key for the homework. I can just say, hey, look at the Q&A.
Sounds good. Well, thank you, Tony. Have a good weekend.
You too. Bye-bye.
Bye.